Hey friends, Callan Bentley here. I'm at Ragged Mountain Reservoir, which is in the Ragged Mountains near Charlottesville, and is a really nice place to go birding and go hiking. As you can see here from this plaque, the reservoir was dedicated in 2014, and this was done in the usual way where they took a pre-existing drainage, dendritic drainage, and then dammed it. I'm walking across the dam now. It's a pretty nice dam trail. But then that impounded water, and then they use that as a reservoir for drinking water for Charlottesville. I'm on my way to a spot where you can see some of the rocks here exposed, and they're pretty fresh. It's the reservoir's emergency spillway. So most of the water that leaves the reservoir goes through a pipe, of course, an outtake. But if there was a period of excessive rain, then the excess water could flow out through the emergency spillway, and there's some nice rocks exposed there. So that's worth our time and our attention to go and take a look at those rocks. Gotten on the trail here on my way to the spillway. So basically, after you cross the dam, the trail is on the left, and it's a short distance to walk down that trail to this emergency spillway site. Okay, you know you're getting to the spill when you come up to the big sign kiosk with no sign on it. And then this thing here is the spillway, believe it or not. The weeds have gotten pretty high. You can see over there, there's some rock. And that rock is interesting and worthy of your attention. However, you should in no way, shape, or form access that rock. Okay, so here I am next to the rock. This rock is interesting, and it actually is our local representative of the oldest rocks in Virginia, the oldest rocks in the Blue Ridge Geologic Province, which hosts the oldest rocks in Virginia. This is one bit of the Blue Ridge Basement Complex, all right? If you take a look at it here, you'll see that it's an intrusive igneous rock, a plutonic rock, and it's got a lot of variation to it. So most of the rock here is this biotite granite, which has this sort of mix of light and dark minerals. But then in certain places here, you'll be able to see things that look significantly darker. This is an example of what's called a microgranular mafic enclave. And so within an overall felsic or intermediate rock, sometimes you'll get these little blobs of darker colored material that tend to have a finer grained texture. And they are present in several places here. These are examples of little blobs of mafic magma that failed to mix with the overall surrounding more felsic magma. So just like the blobs in a lava lamp, they floated independently, and then they crystallized earlier and ended up getting a finer grained texture as a result. Here's something else that presents a complication. This stripe of light colored material here. This is what you might call a pegmatite dike, or you might call a vein of quartz. It's mostly quartz, but in a few places here you can also see feldspar, like right here where I'm pointing. And there are even little chunks of biotite-rich surrounding rock that basically have dropped into the empty space that opened up to make this dike. So you can't crack the rock and make a dike unless the rock already exists. So this surrounding biotite granite had to crystallize first, and then a crack had to open up into which juicy fluids got sucked, and even some little solid chunks got pulled in there as well. And then that crack got sealed shut by minerals in those juicy fluids, a lot of which were milky quartz. So it was a very silica-rich fluid. Here's another interesting feature which kind of confuses me. So here in the middle of sort of the darker colored background plutonic igneous rock, there's this zone here that is lighter colored and has more of a speckled appearance to it. And I'm not sure what this thing is. I'm not sure whether in 3 dimensions, whether this is a tube or a sphere or some other shape. But this could be a magmatic flow structure, or it could be a highly altered xenolith within the magma chamber. There are a lot of these dark colored surfaces. You can see that this looks really prominent from that angle, but then if you go around here, you can see it's super thin, and then there's another one here, and another one here, another one here. If we go over here, there's one here. These are fracture surfaces that seem to be mineralized, and this one here that I'm pointing at, I actually feel like I can see some slick insides in there that seem to show a little bit of shearing motion on this fracture surface. So these may be late stage features or deformational features that are associated to later tectonic stresses that were enjoyed by these rocks. Here's another interesting little zone here where we have evidence of some deformation. So here's the sort of equigranular texture that we would expect to see in a plutonic igneous rock. But then right here, there's this zone where the grains seem to be smaller in size and more stretched out into these elongated shapes that run kind of this way. So this seems to be a small shear zone that is overprinting the equigranular plutonic texture. And that seems to coincide with this vein right here. So in particular, right here, you can see that the vein has some of these stretched out minerals in it. So it could be that a little shear zone nucleated against a pre-existing igneous dike. All right, we've come a little bit further along the outcrop here, and I'm now about halfway down the emergency spillway. And if you look right here, you can see the contact between two different flavors of granite. A more coarse-grained version that's up above and it's kind of darker colored, and then a finer-grained version that's lighter colored down below. So this is an igneous contact here, an intrusive igneous contact, and suggests that there were multiple different compositions of magma that were intruding into this spot and overlapping one another in space, if not in time. The question of time actually brings up something really important here, which is how old these granite and granitoid rocks are. The answer to that is that these are all Mesoproterozoic in age. They're related to the episode of mountain building called the Grenville orogeny that we think was associated with the development of an early supercontinent called Rodinia. And in this part of Virginia, the dates that we get out of these rocks are around 1.1 billion years old to around 1.0 billion years old. So these are rocks that formed deep in the crust due to the intrusion of felsic and intermediate composition magmas that cooled slowly underground for a long amount of time, and then only later were brought up to Earth's surface. Now, I've mentioned Rodinia, but you might not have heard of Rodinia. You might have heard of the more recent supercontinent called Pangaea. Rodinia formed prior to Pangaea, and it was when Rodinia broke apart and its various continental fragments went skittering over the face of the globe. Then eventually those came back together and crashed into one another. That's when Pangaea got formed. And then most people start their understanding of plate tectonics with the breakup of Pangaea. All right, but one of the great things about the Commonwealth of Virginia is that we record this really tremendous deep time perspective on the construction and destruction of supercontinents like Rodinia and Pangaea. So these rocks were formed when the earlier supercontinent got put together. All right, these are the sorts of rocks we would expect to see forming today underneath the Andes or the Himalayas. All right, rocks that are produced through the partial melting of other rocks. The easiest to melt minerals leak out, and then those go and they find themselves a happy place in the crust where they cool down and they crystallize. Here's another one of these interesting zones of variation where we've got these really dark stripes that seem to be super biotite rich. And you might think that those are screens of some metamorphic rock that were intruded by the magma, but it gets really complicated right here. So you can see that there's actually granitic looking material in the middle, and then there's sort of this fabric where the foliation kind of turns and changes its orientation, almost like an SC fabric running through there. And then if you head up this way, you don't have to go far, and then it just kind of runs out and stops. There are a couple of these vertical drill holes here, and you don't need to pay any attention to those because those are just related to the construction of the spillway. But yeah, another sort of shear zone slash intrusive dike. And then one of the things that's kind of cool right here is you can see there's a fracture that runs across the field of view, and that fracture is offsetting this interesting dike shear zone complex, with the far side moving to the left relative to the near side, or at least apparently left lateral offset. And if you wanted to confirm that, you could go and look for slickened sides on surfaces like this one here. So if this is indeed a fault zone, you might expect to see some lineations there showing the direction of transport. But I don't see any, which is sometimes the way it works out. Here's a boulder by the dam that shows some of these complicated relationships. The overall rock here is a dark colored rock, a biotite granite or something approaching a diorite in its coloration. But then you can see here that it's cut across by this seam, basically starts here and goes across to a right here, of much whiter granite. All right, so that's a dike of what I would probably call aplite because of its fine-grained texture. Now I've moved just a little bit further down the face of the outcrop, and there's something new and pretty exciting right here. So my hand right now is on some of these Grenvillian granitoids, and then right here, suddenly we jump over to a brand new rock type. You can see it's much finer grained than the granite we were just looking at, and it is much darker in color. It's darker colored and it's finer grained. We call that a basalt. And basalt typically has a very different origin tectonically than does granite. Basalt is what you get when you partially melt Earth's mantle. And you can partially melt Earth's mantle a couple different ways. Intriguingly enough, not usually by heating it up, but instead by adding water to it, which lowers the melting temperature, or by decompressing it. And so I'm going to go with hypothesis number 2 here, decompression. And that suggests that at some point in the history of Virginia, the crust stretched, and as it stretched, it thinned out, and as it thinned out, it decompressed the underlying mantle, which then leaked out a brand new batch of mafic lava, mafic magma, and then that mafic magma moved up through cracks in the crust and then made its way up to the Earth's surface, where it erupted as a series of lava flows. So this is what we call a feeder dike. We interpret it as the plumbing that fed surface lava flows during the breakup of Rodinia and the birth of a brand new ocean basin called the Iapetus Ocean. The other side of the feeder dike is not so easy to spot. You can see it's all covered with vegetation here, but if you go past the vegetation, you see more of our granites over on the far side. Okay, I'm over on the other side of the outcrop now, and you can see I've got a couple of friends here who've moved in to help me tell the story. Here's one praying mantis, and here's another praying mantis. And those praying mantises are walking up another dike of lighter colored granite. In fact, this lighter colored granite is kind of sugary in its texture, fairly fine grained, especially as you compare it to the surrounding material. And so we might call this an aplite dike. Aplite is just a trade term for finer grained granites, often intruded late in the game in terms of magmatic intrusion. Just look at the variety of different textures and colors that you see in this one little outcrop here. You can see this sort of dark stain, this rusty looking color that's coming down from up above here. Definitely looks like there was some hydrothermal alteration of these rocks, producing rusting of the biotite and maybe other iron-rich minerals. One of the more intriguing aspects of this spillway outcrop is right here behind me. I've moved over to the other side, I guess the eastern side of the spillway, the west-facing side. I'm here in the afternoon. You can see the sun's hitting me right in the face. But here behind me, you can see there's this zone that is altered. So we've got those yellows and browns that suggest hydrothermal fluid flow. But more than that, it's also got a pretty pronounced foliation. So if you look closely at the rocks here, you'll see that they have smaller minerals that are flattened and aligned in a common direction. And that suggests that this is the deep equivalent of a fault, also called a shear zone. And so these rocks have been myelinitized, which is to say they've been sheared out under high temperatures and pressures, and it's produced a different texture to the rock. So this myelinite was first described by Charles Lapworth at Loch Eriboll in Scotland, where he realized that it was the signature of faulting. Even though it wasn't crushed up rock, it was basically smeared out rock instead. Not all faults happen up near Earth's surface. Some happened at fairly great depth, where the rocks can behave more ductily. So the individual minerals can smear out, or maybe if they're tough, chunky minerals like feldspar, they can break into smaller pieces. But in general, these shear zones that we see running through the Blue Ridge Basement Complex, these tend to be Paleozoic in age. They're much younger than anything else we see here at this outcrop. And they tell us about the tectonic forces that helped close the Iapetus Ocean and make the supercontinent of Pangaea. In other words, this is evidence of the Alleghenian orogeny. I'm back on the trail and hiking further. Let's see, this would be clockwise around the Ragged Mountain Reservoir. I have just finished climbing a hill, which is why I'm huffing and puffing a little bit. But I'm on my way to a place called the Floating Bridge. And this is a spot where, for whatever reason, when they were designing this trail network, they decided rather than just going around the last little bit of shore, they would put a series of pontoons out onto the reservoir and have people walk across the bridge that floats on those pontoons. So that's fine. As we're walking along here, I just spotted something. This is kind of cool. So here's another example of an aplite dike. And so we've got an aplite dike that kind of goes like this. Actually kind of cool because it makes a little bend here, a little kink. But that again disrupts the darker colored, coarser grained granite on either side. Anyhow, the floating bridge is a place where we can see a couple more aspects of the Grenvillian intrusive complex, and then again a little bit of the much later Paleozoic age deformational overprint on these rocks. So that's where we're off to next. Well, this is the outcrop that I wanted to show you. It is kind of harshly lit at the moment with some pretty strong sunlight and also some fairly strong shadows. But if you look right here, you'll see that there's a sharp contact there between a coarser, darker granite and a finer, lighter colored granite. And that's something, of course, that we've seen several times already. And in addition to that, you can see there's a little patch right here where some of the weathered rock has actually spalled off, exfoliated from the outcrop. And so you can get a look at a relatively fresh surface there. That's exactly the same stuff as is right here, but here it's covered up with, you know, the East Coast equivalent of desert varnish and mildew and lichen and mold. And here it's a little bit fresher. I bet if we searched around down here below the outcrop, we could actually find the little flake that popped off there. One of the things that catches my eye there is there's actually a bit of foliation. In other words, this is probably one of the older Grenvillian granites because it's been squeezed a bit by the forces of Grenvillian mountain building, and that's caused the minerals to line up into a metamorphic foliation. The other thing that's striking right here is if you follow this contact between the two granites up, you can see that suddenly it jumps over a bit right here and then continues to go up along the outcrop like that. All right, so if you follow that down, you can see that suddenly it steps over right here. So there's a fracture system that runs right along that same zone, and I think that's another small fault, a small offset fault. And we rapidly lose sight of it here going into the fine-grained granite on the right, because it's just not as obvious when the rock on either side of the fault looks the same. It also looks pretty well annealed, and that may be an indication that that faulting happened when this was still a relatively warm, young body of rock, rather than a old, cold, brittle body of rock. One more place I'd like to show you is the Peninsula Trail. And the Peninsula Trail leads out onto this skinny little peninsula that pokes like a finger out into the main reservoir. Kind of a different vegetation suite out here. A lot of locust trees and tall grasses, but there are some additional outcrops too. Here's one of these outcrops, and then another there, and another poking up there, and then a great big one back this way. All right, so here's one of these outcrops, and one of the things that's kind of neat right here is you can actually see some garnets in these granites, these little red balls that show up here and there throughout the body of the rock. And that suggests a composition that would be aluminum rich, so-called paraluminous granite, probably indicating a sedimentary source for the partial melting that made the granite. Here's another one of these slightly foliated biotite-rich granites, and you can see there it's very nicely lit by the sun from the west, and there's a couple of nice aplite dikes that cut across it there, 1 and 2. So again, a fairly typical representative of the sort of stuff we have here at Ragged Mountain. So I'm heading on back on the Peninsula Trail, and I'm walking over these pavement outcrops here, and they're kind of cool actually. I didn't really plan to stop and look at them, but they actually show something kind of neat, and that is weathering. All right, so if you take a look here, you can see some nice fresh surfaces of granite here, and then we've got these sort of weathered surfaces that have lots of sort of dark colored scuzz growing on them. But what I'm noticing here is this stuff, sort of accumulating in the low spots in the outcrop are these very coarse feldspar-rich sediments, the sort of thing that you might call a grus. And this grus, if you accumulated a lot of it and lithified it, would make the sedimentary rock called an arkose. All right, it's a fairly immature sedimentary package because the feldspar in it hasn't rotted away to make clay. And in fact, the next unit up in the stratigraphic sequence is an arkose. So I hope you'll join me in a future episode of this field trip series when we go and we look at that arkose in western Charlottesville. Down here by the boat launch area, there's a couple of sheds, and behind these sheds there's a little bit of rock outcrop there, and that's worth taking a look at as well. There are a bunch of different textures here. One you can see here is sort of dominated by fine-grained mafic minerals and has a few light-colored plagioclases. And then there's another one just here that seems to be more of a finer-grained texture. Oh, there's a little shear band running through that one. That's kind of cool. And up here you can see again sort of two fine-grained textures, one more felsic, one more mafic. Some other shear bands running through right here. One more thing I wanted to call your attention to is in this boulder here that's just to the left as you walk past the exit gate. If you look carefully out right here, you can see there's a zone of highly foliated rock, about 1 centimeter wide. It's another one of these small shear zones that cuts through the rock and is probably of Paleozoic age. All right, Ragged Mountain, it's been real. Thanks for showing us your secrets.